This is chapter 10-6. We're talking about circles and arcs. And the topics that we have to cover is identifying parts of a circle, the measures of central angles, which we're going to, for this presentation, be measuring in degrees, and the measures of arcs, which is the same thing as measuring a central angle. And then we're going to talk about circumference and arc length, which is we have to make sure that we understand there's a difference. That these topics we're talking about degrees for measure, and these topics in blue we're talking about length. Okay, so here's a circle. The center of the circle is the point A, so that's designated with a capital A, so we refer to this as circle A. And the radius is a line segment that runs from the center of the circle to the outside edge of the circle. In this case, I labeled the point B where it intersects. So the line segment AB is the radius. And the circle itself is all points that are equidistant from the center of the circle A that have the same distance that, of the length of AB. Now, okay, if this is the radius, then if I draw a diameter, so if I pick a point and let's just call this D and call this point E, then DE, and it passes through the center of the circle. DE is a chord that passes through the center of the circle, and so that's a diameter. And the diameter is going to be double the radius. So if I arbitrarily just say that radius AB, the length is 5, so if I say that AB is equal to 5, nice handwriting, then that would mean that DE has to be equal to double that, which would be 10. Okay, and down here I drew another circle, so if I gave that a center point of Z, we would refer to that circle as circle Z. Okay, central angles. BAC, going from B, vertex is A, which is the center of the circle, that's the big deal, central angle, center of the circle, C. Then BAC is the central angle, okay? And we would measure that degree opening there. Let's move on. And then the two intersection points of the central angle on the circle itself, BC, that would be called an arc. Think of it like a pizza crust. So the measure of this arc, BC, is going to be the same measure in degrees of the central angle, BAC. Okay. And okay, my software, Math Illustrations gave it this value. We're going to round it up to 55 for this presentation. Now, this angle BAC, this central angle, is 55 degrees. So then, as I said, the arc, same intersection letters in the end. Look, BC, arc, BC, BC. This is going to be 55 degrees for a measure. Okay, now if we go to a major arc, that means that we're not taking, let me back up. A minor arc takes the shortest path between the 2 points that are designated BC. The shortest path along the edge of the circle is the way to phrase it. So this is BC. Now a major arc is going to take the longer way around. And so you need a third letter to force us to go that way. So it's B, D, C. BDC is a major arc. And if we picked a different letter, let's put in an E over here. Well then, BEC would be the same major arc. Same end letters. Now, if we knew before that this was 55 degrees, and we know that a circle going all the way around in degrees for a circle is 360, well then 360 minus 55 is going to give you 305 degrees, and that's going to be the measure of that major arc. So the major arc BDC is 305 degrees. Okay, more notation. BE is a diameter, passes through the center of the circle, and if we go what looks like a major arc BDE, BDE, looks like it because it has 3 letters with the arc symbol across the top. I forgot to say that before. This curvy little arc symbol is important. BDE is a semicircle because it goes halfway around a circle. So it's half of a circle. So it's 180 degrees. Now, we have another arc going this way, which is going to be BCE. That's another semicircle, and that's going to be 180 degrees as well. What I wanted to point out is that if this is 55 degrees, and then this is half of a circle, 180 degrees, this part here must be 125 degrees, and these two they're adjacent. You can add them together to create the 180 degrees. Okay, next frame. Circles are similar. They have the same shape. They're obviously both circles, and that means they're proportional. So circle A is proportional, same shape as circle B. Concentric circles, those are circles that share the same center. And so it's a little awkward then to call this small circle circle A and this larger circle circle A. So we could use subscript and call this circle 1 and call this circle 2. A little awkward. Okay, circumference of a circle. We're sort of done talking about degrees. Before we were talking about measures of central angles, degrees. Now we're talking about length. So circumference is like perimeter. So how long is it to go around the circle? And so the formula is going to be 2 pi r, or if you think about it, double the radius is the diameter. So it could be diameter times pi. Same thing. So if we just said that the radius was 5 units, then we would place that value of 5 in for the variable for r. Evaluate the expression such that r is 5. And so then you're going to have, well, that's 10 pi units. And if you want, we could put the 3.14 in place of the pi to get an approximation. So 3.14 times 10 is going to give us 31.4 units. And that's an approximate, so we got the little squiggly marks in front of it. Okay, I grabbed these examples off of CUDA software, and I typed this up for you ahead of time so you wouldn't have to deal with my horrible handwriting. So if the circumference is 2 pi r, and we can see the radius is 10 kilometers, it's going to be 2 pi 10 kilometers, which is 20 pi kilometers. And I put the equality symbol because that's exact. And then if you put 3.14 as an approximation for pi, swigglies, it's going to approximate to 62.8 kilometers. This example to the right is to make sure we understand the difference between diameter and radius. This diameter, this 10 kilometers, was placed in the middle, this radius was placed clearly in the middle of this radius. Whereas this diameter, this 10 kilometers, is in the middle of the diameter. So then we need to notice that this portion here is half, 9 kilometers, and this portion here is 9 kilometers. So the radius is 9. So it's 2 pi 9 kilometers, which is going to be 18 pi kilometers. And if you want to put the 3.14 in to approximate, you're going to get 56.5 kilometers. Okay. Arc length. This is very much related to circumference. It's how long the arc is. But we're not dealing with a whole circle, but we're dealing with a proportion of a circle. So if we look at this illustration to the left, this looks like about 3/4 of a circle, and it is. So it's going to be 3/4 times whatever that circumference is. So that would be 2 pi, and the radius would be 8. So that's the setup. And that reduces to 12 pi as shown here. Let's make this more formal for a description. The measure of this major arc is 270 degrees. And if it's 270, I should write that, 270 degrees from here around to here. So if it's 270 degrees, then the proportion of this arc out of the whole circle is going to be 270 out of 360 degrees times the circumference, which gives you the same answer, 12 pi. And there's the decimal approximation. Okay, next one. So our example in the beginning of this discussion was that arc BC was 55 degrees. And so I put a radius of 9. So then the setup for finding out the length of BC is going to be 55 out of 360, that's your proportion, times the circumference, which is 2 pi 9, which is going to be 18 pi. The 55 over 360 does reduce down to 11 over 72. How did I get that? Dividing the top and the bottom both by 5. And then you can see that that's an even number and that's an even number. That's clearly can be reduced. and this does reduce down to, you multiply across here, some students forget that. That's going to be 18 times 11 with the 72 times 1 in the base, in the denominator. So that reduces down to 11 over 4, and there's the pi along for the ride there. And then 11 over 4, if you want to write it as a decimal, is going to be 2.75, which is pretty sloppy putting a decimal next to a pi symbol, because a decimal gives the illusion of an approximation, and pi gives you the illusion of an exact answer. So this is I like this answer better. I'm not as happy with this one. And then I put the 3.14 in there, so this way you got your approximate answer for those who want that. I wanted to point out again from the beginning of the lesson, measures of arcs is in degrees. So the measure of this blue arc is the same as the measure of, the measure of this red arc is the same as this measure of the blue one. But clearly the blue arc is longer, so arc length is different than measuring the arcs. And then, let's see, we've got to name central angles. Let me hit pause here for a second. I got to say why I said pause. Say goodnight, Mason.
Good night.
There you go. Okay, so that was my grandson. Let's keep going here. So, let's see. XV, the arc XV. That arc, well, it has the two endpoints that are intersect at X and V, so that's on the outside of this angle, because we're naming a central angle. And then Q is the center of the circle, so the central angle is going to be XQV. And for EF, well, then the central angle is going to be EQF. So we're done with that. And let's see, if you're given a central angle, AQC, well, then the arc is going to be AC. If you're given BQC, well, then the arc is BC. And the length of this arc, okay, well, the proportion involved with this bold arc here is going to be 135 out of 360, so that's cool. And then we've got 11 feet for the radius, so you plug that into the 2 pi r, so 2 pi 11 feet. And then, let's see, the 135 over 360 reduces to 3/8. 2 times 11, there's your 22. And then 66 over 8 is going to reduce to 33 over 4 with the pi over there. And we're done. Well, and then there's the decimal approximation. Well, let's see what's next. And this arc length, let's see, the measure of the arc is 270, so the proportion is going to be 270 over 360. The radius is 17 kilometers, so it's 2 pi 17 kilometers. And then that reduces down to 51 over 2 pi kilometers. And then there's the decimal approximation as well. And I think that's it. Yes. So here, this is the credits of all the software I used to create this presentation. I used Smart Notebook 11 software. There's the URL to download it. Math Illustrations 3.1 I used. There's the URL to find it as well, to download it. And Math Type. And then the final problems, I used Infinite Geometry from CUDA software to create those problems. And the book itself, the 10.6, that chapter number, that's aligned with what the Pearson's book, Pearson Publishing's book, Geometry Common Core. And that's it. Thank you for watching this video.